Good afternoon, everyone, and welcome to the EOL seminar series. Our speaker is another University of Oklahoma graduate student. Chris Rattray will be finishing his master's this spring. His advisor is Dave Parsons, who had a long and hallowed career at NCAR EOL. Chris is a fellow Canadian with an undergraduate degree from the University of Manitoba in physical geography, specializing in atmospheric science. An interesting tidbit is that Chris was president of the Weather Club at the University of Manitoba. So it makes complete sense that he transitioned onward to the School of Meteorology at the University of Oklahoma, which is well known for their severe weather research. In today's seminar, Chris will examine the Nocturnal Low-Level Jet, in particular its evolution in the Great Plains, which encompasses parts of our state of Colorado. EOL is no stranger to the Great Plains. My background screen features a Nebraskan landscape of a photo of a Nebraskan landscape that was taken during the Grey Necks Field Project. We are using Slido to pose questions, which you can ask at any time during the seminar. The Slido window is located at the bottom of the presentation screen. Do not be alarmed if you do not see your question on the Slido window. We are collecting all questions that will be revealed during the Q&A portion of the talk at the end of the presentation. Chris Rattray, we welcome you to EOL, and the virtual stage is yours.
Great. Thank you for that introduction. I would just like to start by thanking my advisors, Drs. David Parsons and Alan Shapiro. And I would also like to thank my colleagues at the University of Oklahoma, Drs. Gebauer, Selesky, and Smith for their help, and also Drs. Weckworth, Luxvec, and Turner for their help interpreting some surface flux data, Risto Chupilski for helping me prepare this, and the participants of the IHOP 2002 field campaign. Okay, so just some background. So it's been known for a long time that over the US Great Plains during the warm season, there's a precipitation maximum that occurs overnight. And not only is this from convection initiating in the late afternoon over the high plains and propagating east, it also is known to initiate over this region. Just one example here, you can see this is a composite of radar data, and we see around 105 degrees west, so this is in the high plains, precipitation initiates, and then on the y-axis we have time, and then later overnight it tends to propagate east. This suggests that there are some mechanisms helping to maintain an environment favorable for convection after solar heating ends. And one of these mechanisms is the Nocturnal Low-Level Jet. The warm season Nocturnal Low-Level Jet occurring over the US Great Plains is known for having a strong southerly component occurring a few hundred meters above ground. And you can see an example of this in this figure. This is what a typical low-level jet profile would look like, where you have a wind maximum occurring several hundred meters above ground and peaking overnight. This is important. This feature is important because it's been identified as an important source of moisture transport over the region. And it has also been associated with convective initiation in recent work. Low-level jets, looking at low-level jet climatology, we see that there's a maximum that occurs around the Oklahoma-Kansas border. And there have been several mechanisms used to explain this maximum in occurrences. There's still debate about the contributions from each of the mechanisms. However, the slope has been identified as a key factor in why this area is favorable. So just looking at some of the mechanisms, these are 4 commonly cited mechanisms used to explain how low-level jets form by boundary layer processes. First, the inertial oscillation, or just IO mechanism. This occurs when daytime heating shuts down and mixing ceases in the boundary layer, causing disruption to the force balances, resulting in the wind vector to undergo an oscillation around the geostrophic wind vector. Second, we have the thermal wind reversal along sloping terrain, or Holton mechanism. This takes place when the surface cools more quickly than upper portions of the boundary layer at night, leading to a thermal wind reversal resulting in a low-level southerly geostrophic wind maximum. And this mechanism assumes uniform heating along the slope. So the third mechanism is uneven heating along the slope. As a result of uneven heating along the slope, this causes a pressure gradient that changes with height, producing a southerly geostrophic wind maximum. Then the fourth mechanism is due to mean seasonal heating along the slope, which creates a southerly low-level geostrophic flow. And the southerly jet results from the IO mechanism superimposed on the southerly background flow. To help explain the southerly wind maximum, work by Shapiro et al., 2016, combined the Blackadar and Holton mechanisms in an analytical model. This was found to produce southerly jets more similar to those observed in US Great Plains. And their results also showed a westerly low-level jet occurring above the southerly low-level jet. And in recent work, this has been confirmed in observations from recent work, including observations from the recent field project, the Plains Elevated Convection at Night, or PCAN. This feature is important because it's been associated with convective initiation. It's been found to create a more favorable environment for mesoscale convective systems by increasing convective available potential energy, or CAPE, and reducing convective inhibition, or SIN, aloft. And the westerly jet has also been found to influence the structure of the southerly low-level jet through advection of the air from the west. So given these recent findings, there's a lack of work that places the Great Plains low-level jet within a synoptic framework that provides some kind of a conceptual model on how the jet returns to the region following passage of a cold front, and how it helps return conditions favorable for convection. So given this motivation, this work will seek to answer what is the day-to-day evolution of the nocturnal low-level jet following a cold front, and how does the low-level jet return conditions favorable for convection. So just taking a quick look at the data and methods used. The primary source of data in this work comes from the 3-hourly radiosonde data taken during the International H2O Field Project, or just IHOP, 2002. And this took place from 13th of May to June 25th, 2002. The configuration of the sites used allow for the calculation of gradients over the central site, Lamont, using a finite differencing technique. And I will try to refer to these sites by their relative locations. So Hillsborough will be the northern site, Bayside is the western site, Morris is the eastern site, Purcell is southern site, and Lamont, of course, is the central site. I will also be looking at some surface flux data, and these also come from ARM sites. For this data, I'm using the northern and central site along with a site to the west located around 100 kilometers north of Bayside. So that's Coldwater, Kansas, shown as the blue dot on that figure. And the observational data will be supplemented using ERA5 reanalysis data from the European Center for Medium Range Weather Prediction. This is hourly data with a 30-kilometer resolution. During IHOP, there were 3 cold fronts, and due to time, this talk will just focus on the evolution after the second cold front that occurred on 5th June. A similar evolution was also observed after the cold front on June 25th, or sorry, May 25th. And in my analysis, I will first provide an overview of the evolution of both the southerly and westerly low-level jet. And then I will provide more detailed analysis on the 8th and the 10th of June. And these dates were selected because there were slight differences between the evolution and destabilization on these nights. And it appears that the distribution of moisture may have contributed to those differences. So just taking an overview. These are overnight profiles of the V component from the central arm site from the 7th, 8th, and 10th. And you can see that at early evening is 0 UTC, and then 12 UTC is around sunrise. From these, you can see that there's intensification that occurs after the cold front. And then, taking a closer look at that, in this figure now, we're still looking at the V component at the central site, and that is the color shading, so that's the full V component. And the contours are the ageostrophic component calculated using sounding data. And so from this figure, we can see that there's a nocturnal intensification of the V component below 2 kilometers. The y-axis is above sea level, so below 2 kilometers above sea level. And this intensification is associated with an ageostrophic enhancement of around 4 meters per second, which is about what we would expect as a result of the inertial oscillation mechanism. And although I don't show the evolution on the first, on the 6th and the 7th of June, from my analysis, it appears that the initial southerly flow is a result of soil moisture and vegetation differences along the slope, which promotes that low-level southerly flow that I described earlier. So now taking a look at the evolution of the westerly low-level jet. Now these figures show the U component. And again, you can see that there's an intensification that occurs overnight. And now the westerly jet is occurring above the southerly jet that I just showed earlier, before. And from these figures, it tends to be located between 500 meters and 2,000 meters above ground. And this is the same as before, except with the U component. You can see that there's, during the day, there's an upslope ageostrophic flow. And at night, we have a ageostrophic component associated with the westerly low-level jet. And that's occurring around 2,000 meters above sea level. And also we do have a similar intensification showing up where in later days we have a more intense westerly low-level jet. And I should also point out that these boundary layer effects are being superimposed on synoptic scale flow. So we would kind of expect that based on synoptic conditions producing stronger westerly flow later on. So just to provide a quick summary of the overview, both the southerly and westerly jets intensified in subsequent days following the passage of the cold front. Now taking a closer look at the evolution on June 8th. So the top figure is as shown before, with the intensification of the V component at the central site. And now the bottom figure shows the southerly geostrophic wind as contours. And the shading, the color shading, is the virtual potential temperature, or I'll just say theta V from now on, the theta V gradient between the western and central site. So in the bottom figure, redder colors mean that it's warmer at the central site, and that the contours are the geostrophic V component calculated using sounding data. And from this, we see the figure on the bottom shows a diurnal intensification of the geostrophic component. So the southerly jet is intensifying into the period as a result of both the ageostrophic component and the geostrophic enhancement. To better understand what's going on, we need to take a look at the thermal gradients along the slope. Notice the intensification on the 8th. We have a stronger theta V gradient reversal that occurs below 2 kilometers above sea level, and it's associated with the change in the geostrophic wind. So to better understand what's driving the gradient reversal, we're going to take a look at the low-level moisture. So the top panel here is the same as shown before, but the bottom panel shows the mixing ratio at the central site is color-filled data, and the contours are the mixing ratio advection at Lamont. And what we can notice from this is that the greatest moistening to the environment at Lamont occurred on the 8th, and we see increase in low-level moisture and increase in geostrophic wind, suggesting that they may be associated. To understand how they may be associated, we're looking now at downwelling long-wave radiation between the Coldwater, Kansas site and the central site. So the cold water is in blue and Lamont is in red. And what we can see from this is that there's a slight divergence between the two profiles, the two downwelling long-wave radiation profiles on the 8th that we don't really see on the other nights. Yeah, just as you can see in this box. So to find out what, so to help find out if this could be contributing to that gradient reversal, we're just going to take a look at some ERA5 data. So now this figure shows the change in surface sensible heat flux from 0 to 6 UTC, and the change in downwelling long-wave radiation at the same time as the color fill. And from this, we can see that there's an area in central Kansas where the greatest change in sensible heat flux overlaps with the greatest decrease in downwelling long-wave radiation. So the contours, so now the contours in this figure are the change in theta V at the surface. And from this, we can see that the area in central Kansas cools by around 9 degrees. And it's located around 700 meters above sea level. While just to the east, we have the northern arm site, where it cools by about 4 degrees over a similar height. So to help determine if this could have had any impacts on the structure of the low-level jet, we're just going to do a quick thermal wind calculation. So we see that the thermal wind calculation says that we would expect a change of 9 meters per second per kilometer to the geostrophic wind over this height. So the wind shear should change by that amount just over that height. And when we compare that to the change in the full wind, we see that we do see a similar change to the wind profile. This is consistent with some work looking at numerical simulations. Work by Fedorovich et al. 2017 found that the ageostrophic component becomes more dominant in later hours when they looked at the evolution of a jet during pecan. And so just going back to our research question, based on this analysis, enhanced low-level moisture is associated with the thermal gradients along the slope. And our thermal wind calculation suggests that it may be contributing to the structure of this elderly low-level jet. So now just moving on to the second question here. So how does it return conditions favorable for convection? So now these are mixing ratio profiles from June 8th. The western site is top left, eastern site top right, northern site bottom left, southern site bottom right. And from these profiles, we can see that deeper moisture originated from the south and moved north. We also see evidence of moisture moving downslope as moisture decreased at the western site in layers below 1.5 kilometers. We also see evidence of ascent taking place at later times in the evening, as you can see from the arrows there. And now looking at Cape, profiles of Cape. So these figures are Cape as a function of height. And from these Cape profiles, we see a trend in destabilization in layers aloft and a west to east trend in destabilization, which is what is consistent with what's been observed with the nocturnal convection and the eastward propagation. This is also consistent with what we looked at in the moisture profiles of the downslope flow of moisture and south to north advection of moisture by the low-level jet. So just to get a better idea of what's going on, this is just looking at the evolution of the SKU-T profile at the central site. And we see that there's this area between 800 and 700 millibars where cooling and moistening took place. And that appears to have contributed to the enhanced CAPE. So when looking at temperature, when we calculate temperature advection using the radiosonde data, it's unable to account for the cooling. And now looking at moisture advection calculated from the radiosonde data, we do see we have positive moisture advection from meridional and in some layers from the zonal. However, it's still insufficient to fully account for that moistening. It does explain, it does help explain some of the moistening though. Just pointing out the layers associated with the moistening in the meridional. You can see a layer associated with the low-level southerly low-level jet, and another spike in moisture advection that may have been associated with the westerly low-level jet at earlier hours overnight. So now, when we look at vertical velocities, and this is calculated from sounding data, we see weak mesoscale, or weak ascent, I shouldn't say mesoscale ascent, weak ascent of about 2 centimeters per second that persisted throughout the night. And if we assume this lasted over a 6-hour period, this could have resulted in about 400 meters of lift, and that would be sufficient to explain the remaining cooling and moistening that we observed at this site. And this ascent appears to also be associated with a westerly low-level jet, as we have a convergence around the same level that it's located at. So going back, just to provide a quick summary of destabilization on June 8th, it appears that to have been the result of both moisture advection and low-level ascent. And it exhibited that west to east trend that I mentioned at the beginning. So now moving on to June 10th. Now looking back at the theta V gradients, if we look at the 10th, we notice there's very prominent gradient reversal that occurs between 1 and 1.5 kilometers above sea level. If we look at the moisture profile, we see between 2 and 3 kilometers above sea level. There's an area of dry advection taking place. And looking at the theta V profile, there's negative theta V gradient. And so that this is similar to other work looking at advection by this westerly low-level jet. If you recall, I mentioned work by Smith et al. That found that the westerly jet could advect a dry boundary layer air from the west, and this could alter southerly low-level jet structure. So this is also confirmed. This is more evidence for this is provided when we look at theta V advection at Lamont, calculated from the sounding data. We see strong advection occurring at heights where we would expect the westerly low-level jet. And when we look at the changes to the southerly low-level jet on the 10th, we see that there's this west change that occurs first at the western site, and it doesn't seem to be occurring at the sites further east at these times shown here. So this is what we would expect if it is advection altering the low-level jet structure. So just to summarize that, based on this analysis, it is likely that theta V advection is contributing to changes in the structure of the southerly low-level jet on this night. Now, taking a look at the, just going to take a look at the destabilization on June 10th. So we see here that we again see that west to east trend in destabilization, and it also, so it's kind of also a northeast trend. And on this date, we have greater magnitudes of destabilization, where CAPE increases by around 1,000 joules per kilogram in layers aloft. So to try and better understand these changes, we'll take a look at the evolution of a skew T diagram at the central site again. From this, we can see that CAPE increased as a result of some moistening around 800 to 700 millibars. And also there's this area of reduced static stability in layers aloft. And again, we see that there is some moisture advection at the level of the southerly low-level jet. And we also see that there's a lot of warm air advection below 4 kilometers above ground, and this is occurring, or it's associated with both the southerly and westerly low-level jets. So now taking a look at vertical velocities, we see that there wasn't any ascent at the earlier times. However, later on in the evening, we have ascent, and it appears to be associated with the westerly low-level jet again. So to get a better idea of what's going on and how that static stability was reduced aloft, I'm just going to take a look at some cross sections from the ERA5 data. Here we see that zonal cross section that I just had earlier, and point B on this map is the western site, so that's Bi-Sci, and to the west, we have a dry line located around 102 degrees west, and a deep and dry boundary layer west of the dry line, and a more moist and shallow boundary layer to the east. And we have the ageostrophic upslope flow. And the pink contours are the vertical velocities. The gray line is the theta V contour. And the black line is the ERA5 boundary layer height. The red arrow is the ageostrophic component of the U-wind. The black arrow is the geostrophic component. And there's a transparent vector that you might be able to make out here, and that is the geostrophic component of the V-wind. So I will just step through these times, and you will see that a collapse of the dry line at 102 west, and you will see moisture stepping through, moisture moving upslope and downslope, and an area of ascent associated with that dry line collapse. And this has been observed in some literature looking at the evolution of the nocturnal dry line. And what we begin to see from this is that the dry boundary layer in the west is moving eastward and over the moist air. So stepping ahead a bit further, one feature becomes evident is that we start seeing ascent at the leading edge of the dry boundary layer that's advecting east. So you can see at around 101 west. And moisture is still going upslope now. And at some point that moisture will begin to retreat back downslope. And we will see that areas at lower levels become more moist downslope. And again, we see that there's that area of reduced static stability moving east, and there's ascent associated with that. And finally, at 12 UTC, we see that now there's an area of lower static stability that now has moved east and over the moist air mass. So just to summarize that, on the 10th, destabilization was associated with the downslope flow of moisture and advection of the elevated mixed layer from the higher train to the west. There was also an area of ascent at the leading edge of the advecting elevated mixed layer. So some work has suggested that QG warm air ascent associated with QG warm air advection might explain that. Also, it's been documented that this ascent associated with a westerly low-level jet. So thank you for listening to my talk, and with that, I can take any questions.
Great. Thank you, Chris, for a wonderful presentation. I appreciate the thorough overview that you gave on nocturnal low-level jets, particularly using a case study and radiosonde data from the IHOP campaign. So we have time for questions. Again, please use the Sligo interface, which is below the presentation screen. We have a question from Chris Cruz. He says, your forcing mechanisms seem to just force a diurnal oscillation of low-level winds, but it seems there's a mean net meridional mass water flux. What forces the mean flow? More DWLR with more moisture to the east, seasonal synoptic forcing?
Yeah, thanks for your question. Yeah, so based on these examples I've looked at, the the water flux it does sort of follow a cycle of a few days where so on the June 5th, we had that cold front come through the region, and it sort of knocked out the moisture, if you will. And then over a few days, that moisture, it took a few days for that moisture to return to the region. And that moisture eventually returned to that region. And from my analysis of soil moisture, it appears that helped promote the soil moisture differences along the slope, helped promote a southerly low-level flow that initially brought a bit of that moisture back. And so I would say that initial moistures from that soil moisture difference along the slope, and I think other works also found the vegetation may also play a role in that. And then as more of that moisture was evected over the sites, we started seeing that dry line. And the dry line in the dates I've looked at, it does show this diurnal cycle where, and this has also been documented in the literature, where it collapses at night, and if you have a strong dry line, some of that moisture will flow up slope for a bit and then come back down. And then this cycle sort of continues until you have another cold front come through. So I hope that answers your question.
Great, thanks for that question and the answer. We have a question from Jørgen Jensen. The ERA 5 analysis appeared to show that the jet occurred both below and above the top of the model diagnosed jet. If nocturnal convection occurs as a result of the low-level jet, is this convection primarily fed by jet air below or above the top of the boundary layer?
This is a good question. I would have to say I don't think I have a good answer for your question. I'm not that familiar with inflow for nocturnal convection. Yeah, I'm sorry, I don't really have a good answer for that. I would like to look into that further, though. So if you're able to get my email address somehow, please feel free to send me email.
Thanks, Jørgen. Thank you, Chris. We have time for more questions, and we're not quite at the hour, so we're going to wait and see if more questions come in. Well, we're a quiet group today. Chris, this tells me that you gave such a complete and comprehensive seminar that everyone understands your presentation, and everyone is now an expert on the methods of low-level jet development. Well done, Chris.
Oh, well, thank you.
Well, if there are no further questions coming in, if you are interested in this research and have further questions, please reach out to Chris via his email, which is provided on the seminar flyer. On behalf of EOL, I would like to thank Chris and wish him good luck in defending his master's. Thank you, everyone, and have a great day.
Thank you.